Okay, let's get started. Any questions, general questions before we start the lecture? Okay, so let me go where we left off last lecture. Last lecture we were talking about the Wide-Widlar reference, and we noted that it's a circuit that is slightly, let's say, somewhat insensitive to supply voltage. If you look at the output current, IC2, which is basically the current through this transistor, it's developed by taking a delta VBE, the difference between these two transistors, VBE, across this resistor. And since delta VBE is relatively small, right? Even a 10x difference in current only gives us about 60 millivolts. This current is also going to be very small. So that's one application of this circuit, is to use it to generate very small currents. But then the observation is that because of this transcendental equation that relates the input and output currents, as we change the reference current by 10x here, you can see that the current through Q2 changes relatively little, right? So that's pretty good. And in fact, there's a way we can make this even better. So here's the way to see how you can make this even more supply insensitive. So you have a transfer function that looks something like this. This is a relationship between IC2 and IC1. And actually, do I get it backwards? No, I think it's right. So what we're going to do is, so this is really the reference current, is what if we somehow force the currents in these two transistors to be equal to each other? Or if you like, you could make them to be some multiple of each other. Well, if you do that, that means that you have to operate along some line, right? Where, for instance, this could be IC1 equals to IC2, or IC1 equals 10 times IC2, or whatever you like. But let's use this simple case of equality. Well, if that's true, then you can see very clearly here that there's only two potential solutions: zero current and some finite value of current. And in fact, if we do this, if we force these currents to be equal to each other, then this is the only solution that will satisfy the circuit. And how do we do that? Well, that's pretty simple. If we go back here to the slides, we can see that a simple current mirror forces the equality in currents, and that actually tells us that that gives us the operating point where this circuit will generate its current. And now this is more or less independent of the supply voltage. Okay. As another way of looking at this, the other way to look at this is this circuit kind of bootstraps itself. The whole problem in this previous circuit is the reference current is a function of the supply voltage. So why not take the output, instead of using a reference that depends on supply, why not use the output of the circuit as its own reference, right? It's kind of a funny concept, right? Take the output of this circuit and then mirror it and make it its own reference. And so then it will not depend on any external reference. It won't depend on supply voltage. Shishi, you have a question?
I don't understand how we get when we're in the I reference, why we get the IC2 curve looks like this. Can you qualitatively explain?
This curve here, where does this come from? This is the solution to this equation. And you can't invert this equation, so you have to solve it numerically. But this is just a result of solving this equation. And it kind of looks like a log, right? If this linear term didn't exist, then it would be a log relationship, right? Yeah. If this term, this term.
Explain it qualitatively why it looks like this.
A good qualitative reason, well, so if this resistor weren't here, right, the currents would equal each other, right? And this resistor forces a linear term, which messes up the logarithmic relationship between here, right? And so this term here forces the current to look like this. I mean, that's the best I can do. Yeah, I don't have a good intuitive. Okay, so this concept of bootstrapping is really positive feedback, right? You're taking the output and bringing it back into the input, and so that sets up a positive feedback loop. And in fact, what you can show is that if we come back to the slide, if we come back to the the notes here, that in fact this circuit does have positive feedback, and if you start anywhere on this curve, the circuit will kick itself and move into this stable point. So this actually is a stable point. It's positive feedback with loop gain less than 1. So that's great. It looks like this circuit here that we've drawn here on the slide will actually kick itself into a very well-known state that's independent of supply voltage. What's the problem with this? First of all, how many people have seen this circuit in 140? Okay, about half the class has seen it in 140. Let me just make a comment. I'm going to go relatively fast through these reference circuits because about half of you have seen them in 140, and for the other half who have not, I encourage you to read Gray and Meyer. I think it's chapter 3 or 4. They're very well covered in Gray and Meyer. So we'll go relatively quickly. We won't work out all the detailed equations. Well, what's the problem? What's a potential problem with this circuit? Lots of people know since they've taken 140. Maybe somebody can guess. Give you a hint, right? There's two potential solutions.
It may not start up correctly.
That's right. What if it falls into this point here, right? If it falls here, it could potentially just stay here. Now, theoretically, if any noise voltage just kicks it enough, right, just noise in the circuit, it should get out of this. It should actually end up going here. So it seems unlikely that the circuit will remain in this dead state. But the problem is that when the circuit is dead, there's no currents flowing, so there is no gain, right? So if you do end up in this zero current state, even a noise voltage that kicks it will not have enough loop gain to get it out of this dead state because the current levels are so low. So in fact, what we need to do is guarantee that we never end up in this dead state, that we always turn ourselves on. So we need a circuit that forces us into this condition. And it's actually very easy to design these so-called startup circuits. So you have a startup circuit. All the startup circuit needs to do is detect a zero current state and then force some current through the transistors, enough current so that it has enough loop gain to get into the right state. Okay. Questions? All right, so let's look at a couple more interesting points here. Another interesting point about this circuit is that this one is worth working out in a little bit of detail because it's going to come up a lot. So in this circuit, I'm forcing the currents in these two transistors to be equal to each other. That means that I have a delta VBE, right, that's being applied across R. Now delta VBE is not equal to 0 because I've actually sized these transistors so they're not equal, right? And I could have also scaled the currents and used equal transistors, so I have a choice here. If I had made the transistors equal size, right, there would be no current, right, because delta VBE would be 0. 0 across R would generate no current. So it would not actually work as intended. So what is delta VBE? So let's just calculate that. So delta VBE is, let's say, VBE of 1 minus VBE of 2. So that's VT log of IC1, let's call this Q1, Q2, over IS1, minus VT log of IC2 over IS2. And if I just collect terms here, that's log of IC1 over IC2, IS2 over IS1. And the current mirror forces equality here, so this term goes away. And so we have VT log of IS2 over IS1. So what's IS2 over IS1? It's just M, right? It's this factor M. It's a ratio between the areas of these transistors. In this case, I've used M identical copies so that m is very precisely equal to m, or n is very precisely equal to m. So this should be Vt log of m, okay, which is a constant. And it's a constant over supply, right, over temperature, and over process. Great. That means that the current I, which is, sorry, this should be delta VBE, which is delta VBE over R, is basically Vt over R log of m. And this is one of the best constants that we can generate on chip. Yes?
It's not really constant over temperature because Vt is kT over Q.
No, m is constant.
Oh, m is.
Yeah. So basically this term here is constant, and exactly this term is kT over Q. So the temperature dependence of this current is in fact proportional to temperature. And that's why we call this circuit a PTAT. It's proportional to absolute temperature. Okay? And this is actually very useful. We can make use of this proportionality to temperature. One, build a thermometer, right? But for another, we can actually take advantage of the, maybe we have something else which is inversely proportional to temperature, or roughly so. And so we can use the temperature coefficient of this current mirror to cancel out the temperature coefficient of something else. For instance, if we were so lucky that R were proportional to temperature in this equation, right, then we would have something that would be temperature independent. Okay. So we see that this circuit here, so here's just some calculations. This is the temperature dependence of VBE. This is the temperature dependence of our circuit. And you can see basically these are very simple equations. You can look at them in detail. So here is, in fact, a way to build a PTAT reference in CMOS technology. The point is that in CMOS we don't have bipolar transistors, right? So if we build bipolars, they're going to be basically N-well bipolars or P-well, depending on the process, if it's a P-well or an P substrate or an N substrate. But what really is unfortunate in a standard generic CMOS process is that we don't really have floating diodes. Every diode we build always has a terminal in the substrate. So for instance here, if I want to build a PNP device, I'm going to use basic NMOS structure, PMOS structure, excuse me. So this is a P substrate, this is my N-well, this is my base contact, my emitter contact, but my collector is actually part of the substrate. So that it's always going to be a grounded collector. Well, that's okay. You can still build bipolar transistors that way, but you just have to make sure that it's not floating, right? Nowadays, in triple well processes, you might have an option of using a triple well process. This problem kind of goes away. Now you actually can have a floating diode, if you like, or actually a transistor with three independent terminals, not grounded. But again, this is the same circuit that we looked at. Again, you have this current mirror that forces equality in currents, and the delta VBE appears across this R, and we get a PTAT just like before. All right, so now this problem with the startup. Let's look at that real quick. So this circuit here is going to somehow detect that there's no current and do something about it. So let's assume that there is no current in M4, right? Let's say that unfortunately we turned on our power supply and it went to this point A. Well, if there's no current in M4, that means there's no current in M5, right? And that current, that zero current, gets mirrored over to M7, and so M7 is operating with no current. M6 is essentially just a resistor. Let's say it's a long channel device, PMOS device, it's a resistor. So this kind of looks like a logic gate. If this current is zero, then this point gets pulled up to supply, right? And if that happens, M9 turns on, right? So now M9 turns on. That's because this point is also about ground, right? Because there's no current in the circuit. So M9 turns on hard and pulls current out of M4. Great. That gets us out of the startup state. Well, that's good because now we're going to go to point B, But we have to make sure that as we move towards point B, the circuit actually turns itself off, right? Otherwise, it's going to mess up the PTAT properties. So let's check that. Well, if the current gets high enough, then this mirrored current gets high enough so that this voltage drops low enough so that M9 turns off, right? So it works. So all you have to do is make sure that over process and temperature, you pick this resistor M6 to be the right value so that the circuit actually turns off, always turns itself off. Okay. Now this is just one way to build a startup circuit. There's tons of different ways of building startup circuits. Okay. Questions or comments? Yes.
I understand this circuit is for CMOS process. What if we replace the bottom PNP with that NPNs and have lower headroom, lower threshold voltage?
So if we just use NPN transistors here,
For the bottom Q1 and Q2?
well, it shouldn't change, right? Because they're just diodes here. So if I use an NPN or PNP, it's a diode-connected transistor, so it doesn't really change anything.
Then you can get rid of the cascode M1, M2, can operate with low voltage.
So your point is, what if you want to reduce the headroom? Yeah. Yeah, in fact, you don't have to use a cascode current mirror, right? The cascode is just used to give us a better supply independence.
For PNP, I guess you have to, right? Because it's for same voltage. For this configuration, you have to use M1, M2.
Yeah, if we go back to this circuit here, right, then if I want to get better performance, I could still use a cascode here, right? It still would improve the performance. So if you're willing to sacrifice performance, yeah, you can go to lower headroom. Is that your point? Yeah. Okay, so all right, so then the next big topic is bandgap references. And again, bandgap references are kind of a big topic, and we could spend a whole lecture on them. But what we're going to do is just highlight how bandgaps work to give you enough background that if you ever need to design a bandgap, you'll go read the right papers and figure out how to design one. So how do bandgaps work? Well, in some ways, a bandgap is very much a logical thing, right? You have somebody probably was thinking, I think maybe it was Wide-Widlar who designed the first bandgap, but the idea was, well, you know, this PTAT current has positive temperature dependence, and if I could find something that had a negative temperature dependence, then I could somehow sum them up and get a zero temperature dependence, right? And in fact, if you're a good bipolar designer, you knew very well that the VBE has a negative temperature dependence, right? That's why we get the current runaway problem in bipolar transistors. So in a bipolar transistor, as we increase temperature, its VBE gets smaller. So if I could somehow sum a VBE, right, I could design a VBE reference current source, do a VBE over R, but that would give me a negative temperature dependence. Well, this PTAT gives me a positive temperature dependence. So if I just sum them together, I could get zero temperature dependence. Okay, and then probably, I'm guessing, when this, you know, when Wide-Widlar or whoever did it first designed this circuit, and they tested it and it worked, felt pretty good about it, and they realized that the voltage they got out was about 1.2 volts. Okay, at the end of the day, when they multiplied a constant times KT over Q and added it to a VBE, and then they started thinking, hey, that's kind of close to the band gap, right? And so then they did some analysis, right? They wrote down some equations, and lo and behold, at the end of the calculation, wow, they produced a band gap voltage, which probably was an accident. But the beauty of it is that you have a circuit that is somehow fundamentally generating a voltage, which is the actual band gap of the crystal. It's pretty exciting. And that also means that because the band gap is relatively universal, right? Anybody who builds a silicon crystal is going to get the same band gap with the same purity levels, right? Then this is actually a very good reference. It doesn't depend on supply. It doesn't depend on temperature. Well, it has a weak temperature dependence. But besides the temperature dependence, it's a pretty universal voltage. So great. You can build a CMOS circuit or a bipolar circuit that generates a very constant voltage over process and voltage, and also over temperature if you have some curvature correction. That's great, but the problem is that we usually need currents, right? We need currents to start up our circuit. So anytime you generate a current, you have to use a resistor. And so that kind of messes everything up, right? If it's very important that you generate a precision current, then you probably have to use, no, you definitely have to use an external resistor that is very precise, with a well-known temperature coefficient, very good precision, and then you can try to compensate, using that resistor, you can try to compensate for the overall temperature dependence of your circuit. Okay.
Question.
Yes.
Why don't you just make an on-chip resistor that has very large area? You know, because external maybe introduce some more, you know, like connection problem. I don't know. Just why don't you just make a very large on-chip resistor?
Well, on chip, the resistivity varies over process, right? So.
Not just the WL, and also the resistivity, right?
Yeah, the resistivity varies a lot. Yeah. Yeah. If it were just a matter of lithography, we could probably do really well, right? Yeah. But sheet resistance of poly varies, sheet resistance of metal layers varies, sheet resistance of the substrate varies. So absolute resistors are very, actually, absolute resistors are very imprecise. Okay, so here are some references for you. Kind of a very old reference, 1971, look in JSSC, also known as red rag. This is the first reported bandgap reference. And then we've got 1991, one that compensates for the offset of an amplifier that you use in a bandgap. We'll see how that comes about momentarily. And then one with improved power supply rejection. What you find in most bandgap circuits is that at low frequencies, they're very independent of power supply, because just like this circuit here that we've designed, to first order it's independent of power supply, but at high frequency capacitances link the power supply to every node in the circuit, and so you get feed through from the supply through these capacitances through the output. So power supply rejection always deteriorates at high frequency. And then finally, we have a couple of more modern references. One that discusses generating a band gap when your supply voltage is less than 1.2 volts. And so here is again the hypothetical band gap that we discussed. Very simple. Take a VBE and sum it with some multiple of KT over Q. We know how to generate KT over Q. That's just our PTAT generator. And again, if you do the detailed physics, you can show that the voltage that you generate is the bandgap voltage plus, this is actually KT over Q, sorry about the bad notation, times some constants. And if you choose your temperature just right, you can make this basically go away. All right. Here is a way to do a band gap in CMOS. The idea is that I'm going to use this op-amp to force the voltage drops across here to be the same, and that means that the voltage across this resistor is a delta VBE, right? And of course we just analyzed that delta VBE gives us the PTAT current, but here let's be a little bit more precise. It's a delta VBE plus the offset voltage of this op-amp, right? No op-amp is perfect. You have to input some kind of voltage to the op-amp to get zero output, right? And so that's the offset voltage. And so this might, depending on the technology and how big you make your input pair, this might be anywhere from millivolts down to microvolts. We'll talk about techniques of improving the offset voltage of op-amps later in the course. But so with this understanding of this offset voltage, if we just carry it around with us, we can at the end correct for this offset voltage. Because if you actually build this circuit, you'll find out that, yeah, it's very temperature independent, except it varies with the temp if you didn't have any offset. But then the temperature dependence of the offset voltage dominates the circuit, so we have to compensate for that. All right, again, I'm not going to go into the details. You can show that the voltage across R2 now is a multiplied version of the voltage across R3 because they have the same current going through them. The multiple is just R2 over R3. And so the output voltage here is basically 1 VBE plus this voltage, which is R2 over R3. So here is the total voltage This is the VEB because it's a PNP device, so this VEB is positive. But so we get the VEB of this device plus this KT over Q term, which is generated by the delta VBE. Okay, so I'll stop here, and if you're interested, you can read the references. Here are some performances that people have achieved with bandgap voltages. This is basically the output voltage they generated, how accurate that output voltage was, what the temperature coefficient that it achieved is, and then what their supply rejection is. And again, it's very important to specify the frequency when you measure power supply rejection. And finally, how much power was dissipated in the circuit. So starting from this reference here, going to this more recent reference, interestingly enough, this more recent reference, using a less than 1 volt supply, generates an output voltage of 0.54, very accurate, about 7.5 ppm per degree C. Fortunately, these units are not the same as these units, so it's hard to compare the power supply rejection. But the power dissipation is very good, very low power dissipation, 100 microwatts. Interestingly enough, I don't have an accuracy number for this one, so we don't know how accurate it is absolutely. But if we compare these accuracies, right, this second reference is 20 millivolt accurate, but only an output voltage of a band gap, right? Whereas this one is 24 millivolts over several band gaps. So definitely 5 band gaps. So this circuit is actually much more accurate in that sense, right? The output voltage varies 20 millivolts relative to 6.2 volts. So definitely this is more accurate than the second one. You can see the power supplies are about the same at low frequencies. Again, without the numbers at high frequencies, it's hard to compare. Okay, questions? So that was a very quick overview of how band gaps work. Again, I encourage you guys to read Gray and Meyer. A lot more details on this, and if you ever do design a band gap, of course you'll become an expert on this. Most companies, if you go work in a company, there's 1 or 2 people in the company who are kind of the reference experts, and so they design all the band gaps and they know all the process corners and all the variations. And so unless you are that person, you probably will rely on someone else to design the band gap for you. But definitely it's good to have the background knowledge in designing band gaps. Another thing that we didn't talk about today, but something to look out for, is if you are comparing different band gaps in the power supply, power dissipation, what other factors should you take into account that's not on this chart here?
The noise?
Yeah, noise. Definitely look at the noise that the band gap generates. And actually, band gaps, you might say band gaps are great, why not use them everywhere? Well, they tend to be fairly noisy, so you have to weigh that against other considerations when you design circuits. All right. Well, here's a final reference circuit that I'll just point out to you guys and let you guys analyze it on your own. You might ask yourself, wait a minute, most of the time I don't care about voltages and currents, I care about GM, right? If I'm designing a small signal circuit, my gain is proportional to GM, my bandwidth is proportional to GM, so really what I want is a circuit that has a constant GM. And here's a way of generating a GM which is actually just inversely proportional to this resistance, where this is again either a precise resistance off chip, or if you can tolerate the variation, some kind of on chip resistance. And the idea is that we're going to generate a delta VGS, right? A delta VGS is a function of overdrive voltage, and force that delta VGS to equal to some IR drop. And if you do that, right, the overdrive voltage of the current is a constant, so we should get a pretty good GM over process and temperature. Okay, so that's going to be any questions? All right, so we're going to now switch topics and start talking about OTAs. And OTAs, if you're not familiar with the terminology, is an operational transconductance amplifier, right? So it's similar to an op-amp, but it's also very different from an op-amp. So the first thing we'd like to do is really compare OTAs and op-amps and clearly understand when we would use an op-amp, when we'd use an OTA. Okay. The next thing we'd like to do, and hopefully by the end of this lecture, is to compare differential operation with single-ended operation and convince you that differential has a lot of benefits. And so if you ever have to decide between differential and single-ended, and it's not the power penalty is not an issue, you should definitely go to differential. And then what we're going to do in the next several lectures is to analyze different OTA topologies. And we'll start out extremely simple. We'll start out with a common source OTA, and then build up into complexity and talk about different kinds of OTAs. Okay, so let's talk about the difference between an OTA and an op-amp. Okay, so maybe I'll first draw an OTA and an op-amp. I think the people who sit around and come up with circuit symbols are very creative people, and they must have a lot of fun with it. So if we look at the symbol for an OTA, can we switch? Yeah. It looks something like this. So of course this is an op-amp. It's a triangle. First of all, why a triangle? Anybody have a good idea of why somebody decided to use a triangle for an amplifier? Right. It's actually kind of fun to sit around and think about all the little schematic symbols and why somebody made them the way they are. So why a triangle?
Maybe it's because unidirectional?
Yeah, it's a unilateral amplifier. The output's only a function of the inputs, not the other way around. And so the triangle kind of emphasizes that there's a direction that the signal flow goes in. Okay. Well, what about this poor OTA? It looks like it's a chopped off version of this device, right? So we chop off the end triangle and we end up with an OTA. Now, when I first saw this symbol, I thought, okay, someone was just trying to distinguish an op-amp between an OTA, because a lot of times people don't. They just draw OTAs like this. That can lead to confusion. But then it dawned on me, she was pointed out to me, that actually there's a good reason for drawing it this way. Anybody have a good guess? Maybe somebody who doesn't know. It's always fun to get the people who don't know to guess on the spot. Why chop off the end of the op-amp? Well, it helps to understand what an OTA is. So let's come back to this question. So an OTA is actually just a transconductance. In other words, what's the world's simplest OTA? Yeah, a transistor, right? A transistor, in fact, the name transistor is transresistor. So this is kind of the world's simplest OTA. Here's my plus and minus terminal, and here's my output terminal. Okay. So clearly this is not a good op-amp, right? If we want to build an op-amp, we probably would use a differential pair. Well, we can do that with an OTA too, but what's wrong with the output of this OTA if we want to make this an op-amp? What are the proper, if you go into SPICE and you make an equivalent circuit for an op-amp, what do you use for the output?
Voltage source.
Yeah, it's a voltage source, right? In other words, it has low impedance. Whereas a transistor has actually high impedance, right? So to turn a transistor into an op-amp, we need an output stage. And maybe we use a source follower or something, right? So now I have the world's cheapest op-amp. This is my output stage. It's pretty low impedance if I run enough current through this. Okay. An OTA, I don't need this output stage, right? Because an OTA is a transconductance amplifier. And so the output impedance is actually high impedance. Right? So now does someone have an idea, good idea for why I draw an OTA like this? Anybody want to take a guess now? Frank, do you raise your hand? Okay. Essentially, an op-amp really is an OTA plus a buffer stage, right? So this is actually an op-amp. It has an OTA, and then it has a buffer. That buffers my high impedance point to a low impedance point. So really, so this is an op-amp, and if I chop off the end of an op-amp, I get an OTA. So really, the symbol has a lot of analogy to it. Okay, so let's go back and look at this chart now. We can now understand some of these elements better. First of all, an op-amp has a voltage source output. We just noted that. OTA has a current source output. It's a high impedance. Op-amps, if you think about it, why is it that we have a voltage source output in an op-amp? Well, first of all, if you want to drive a resistive load, then you need a buffer, right? Why do I need a buffer if I want to drive a resistive load in an op-amp? What happens to an OTA if you drive a resistive load? Okay. Anybody? Use the mic.
You load the current source?
Okay, and why is that bad?
Current you supply is a function of the load, and it's not a constant.
Well, if I'm designing an op-amp, what are some of the what is the main ingredients of an op-amp? What do I really need out of an op-amp? Right? I need a lot of gain. Right? Op-amps have humongous amount of gain. So if op-amps didn't have buffers and I put a resistive load at the output, the gain would just drop down to very low value, right? Because an op-amp, the way we build an op-amp with an OTA is there's an internal point that has very high impedance, so that our GM times capital R is huge. So that buffer is actually to protect that high impedance node. So if I told you I don't ever need to drive resistive loads, then you might say, okay, maybe I don't need that buffer. You would start to question the use of that buffer. So coming back here, we see that an OTA cannot drive a resistive load. Okay, it's not designed to drive resistive loads. If you do it, you'll pay the price. If we can't drive resistive loads, that means our feedback can't be resistive, right? Because a resistive feedback network actually will load the output of our OTA. So that means that we're going to have to use capacitive feedback. Okay, and we'll talk about that a lot more. Okay, so this is a bird's eye view of OTA versus op-amp. Here's another couple of issues. One of the nice things about an op-amp is that the internal gain of the op-amp is independent of the feedback network, right? That's in fact why we use a buffer, so that when you put resistors in the feedback network, you don't load the internal nodes. That buffer is protecting the internal nodes of the amplifier. Okay? In an OTA, because the resistive feedback lowers the gain, we could either use very large resistors, right? That would be one option. But using large resistors means lots of area, as we know very well now. And also, we would have some problems with the parasitics of those large resistors. Large resistors have lots of capacitance, and so the stability of our amplifier would be an issue. On the other hand, if we use capacitive feedback, so let me just draw this. So here's an inverting stage with capacitive feedback. What's the problem with using capacitive feedback? Yes?
At DC, the capacitor looks like an open circuit, so there's no feedback at DC.
That's right. There is no... First of all, this circuit doesn't work at DC, right? And the other issue is that this node, right, this is a high impedance input. And so there's no current going into this node. So what's the voltage at this node? Right? It's kind of unknown. It's determined by leakage in the circuit. So the voltage at this node, because there's no DC feedback, is pretty much an unknown. And so somehow I have to actually, if I care about charges in my circuit, and we'll see very soon that that's actually very relevant, then the fact that I have leakage here, let's say R leak, means that there's going to be some unknown charge accumulating on this node. So what's the solution? Yeah, switches, right? I could actually discharge these capacitors right before I use the circuit, which means I actually need a clock, right? So really, this circuit, as I've shown it, unless I use resistors or unless I don't care about DC, will not work in a continuous fashion. I need to somehow stop the circuit, initialize the capacitors to a proper value, and then let the circuit run again. Okay? So it's really going to be a switch capacitor circuit. So we would say that this is a switch capacitor gain block. Okay? The other nice thing about using switch capacitor operation is that in a typical CMOS process, capacitors ratios are very well defined, right? I can design very precise capacitors, whereas designing resistors tends to take more area and also be less precise. The other interesting thing about these circuits is that the reason that they're so popular now is that historically all analog circuit processing was done in a continuous time, and the signal was never discretized, right? It was never digitized. If you're building today, if you build analog circuits, inevitably they sit in front of some digital circuits, right? And so you know that at some clock rate with some resolution, the signal is going to get digitized. So that kind of gives you the freedom to also run your analog circuits in discrete time. There's no reason why you have to run your analog circuits in continuous time. So if you're going to use, so what can you do in discrete time? Well, one thing you could do, for instance, let's just think, why would it be an advantage to work in discrete time? Well, for instance, you could just turn off all the circuits, turn them on, capture the signal, and then turn off again. That would be one advantage, right? So every clock edge, your circuit could turn on, do something with the signal, and then turn off again. Well, that definitely you could do that if the clock is slow enough, right? If you're in an application where the circuit turns on and settles fast, much faster than the clock rate, then discrete time can be lower power. Unfortunately, we're usually going to be operating at clocking it at very high speed, and so we're going to end up actually trying to design really fast analog circuits that can keep up with that clock without dissipating too much power, of course. Okay, we'll come back to this more. Let me just move ahead now. All right, so what about noise? Okay, and a very interesting question is, what's the noise penalty of using an OTA versus using an op-amp? Okay, let me switch the slide. So we'd like to know what, basically, let's say we're going to end up driving, at the end of the day, we're going to end up sampling our signal. So the output of this amplifier is going to get sampled, right? And so we know that if we sample with an ideal switch, the noise that we get is KT over C, right? So now the question is, what happens if I sample with an amplifier, right? And in particular, I want to compare sampling with an op-amp to sampling with an OTA. And what I'd like to convince you guys of is that actually an OTA is a better choice. So let's see how that works. Okay, so again, the comparison is kind of hard to do. It's a hard comparison to make, but we can kind of say the best case scenario would look something like this. So this is the circuit that I'm going to use to basically sample, and I'm going to make several simplifying assumptions. So this is my buffer. I'm going to assume that somehow I know how to design a buffer with zero noise. Okay? So then the only noise that this circuit is going to have is going to be the noise of this OTA block. Okay? So what's the noise equivalent circuit for this? Well, I have the equivalent output noise of this stage, which is 4kT over GM of the device. And then I don't have any noise in my buffer, so then I'll have the noise of the switch. And then I'll have R switch, and then C. Okay? So if I now actually look at the noise generated by my noise generators, and I integrate from 0 to infinity with a low-pass transfer characteristic, what do I get? Do I get KT over C? Why is it more? Well, remember, when we got the result KT over C, we got it because the noise bandwidth canceled out the amount of noise being generated, right? So the R term went away. So if I actually generate noise with resistance R, and R also sets the bandwidth, then R drops out and we get KT over C. But here in this circuit, you can see that actually I'm generating more noise than just the resistor. And so at the end of the day, what I get is increased noise with a factor of 1 plus the noise of the extra noise I'm generating divided by the noise of the switch. Okay? That makes sense to everybody? So in fact, this buffer messed things up for us, right? Because the buffer changed the impedance level looking back here, right? So now let's see what happens when... So the idea now is that the impedance looking into here is approximately 0 ohms because of the buffer. But the noise is not equal to 0. The noise is just the noise generator of this guy. Well, what about using an OTA? Again, I'll use the same circuit, but now no buffer. And if I draw the noise equivalent circuit, again, I have the noise of this guy, which is 4kT 1 over GM. Then I have the noise of the switch, 4kT R switch. And then I have the output impedance of this guy. What's the output impedance of this OTA? Anybody? Somebody use the mic? I think I heard it over here.
Yeah, is that 1 over GM?
Yeah, it's basically configured in unity gain configuration, right? So its output voltage is equal to the input voltage. The output current is GM times the input current, which is also the output current. So this is actually 1 over GM, and then this is R switch, and then this is C. So what's the total noise generated here? Yeah, everybody knows the answer now because it's just KT over C because the amount of noise is equal to the amount of resistance I have. So the bandwidth, in effect, the noise bandwidth compensates perfectly for the amount of noise being generated. Okay? So that's actually another good reason to use an OTA because I'm going to be designing switched capacitor circuits anyway. What I really care about is this KT over C noise. And if I use a buffer, I mess things up. I actually would prefer not to use a buffer in order to get the best noise. Now, this is a very simplified calculation. So, of course, if you do the calculation more precisely, you'll find the noise is slightly higher than this, right? Because we ignored a lot of details of the noise of this device. But definitely the result is the same. That actually the OTA does have lower noise. Okay. Okay, so now let's see how we can build some useful circuits using an OTA. And so let's actually look at this in a little bit more detail. So this is actually a more complete circuit diagram of an OTA. What we're going to do is put in a lot of switches, and then we'll explain how these switches work. And in fact, this is just one way of doing it. So one of the first observations is that I'm going to use two different clock domains. Okay, so these are basically switches. Of course, we're going to design them with MOSFETs. For now, let's just assume they're ideal switches. And let's say that I have two different clocks. Clock cycle Phi1 and clock cycle, actually this should be Phi1. Yeah, Phi1. That's an error in the slide. And then here I'm going to go with Phi1, Phi1, Phi2, Phi2. Okay. And I'll call this CF and I'll call this CS. Okay, so lots of switches. It looks complicated. But what we'd like, one way to understand how these circuits work is to actually draw the circuit in each clock domain. So what are the two different clock domains? So I'm going to have a clock domain 1 does something like this. Actually, so this is Phi1. And then I'm going to have another clock domain which is Phi2. And one thing that I want to emphasize is that the clocks are non-overlapping. In other words, I turn off this switch, then I turn on this other switch. There's no time period where they're both on, right? And that's important, as we'll see later. Okay, so let's analyze this circuit. Before I do that, I just want to make sure that this circuit diagram is clear to everybody. So any questions about this circuit diagram? Okay, good. So what we're going to do is actually draw the circuit in each phase. Okay. So let's draw phase 1. So this is Phi1 is basically high, Phi2 is low. Okay. So that means every switch clocked with phase 1 clock is actually going to be shorted, and every switch clocked with phase 2 is an open. Okay. And here, this is my input voltage, V input. So this is V input. You can see it's shorted across here into CS, and then CS is grounded. So CS is actually not even connected to the amplifier. Then my amplifier is actually also grounded in unity gain mode. So the output capacitance is discharged through this path. Okay, so I can actually redraw this like that. So my op amp, my OTA, is in unity gain mode, but with the output shorted. Is this okay? Is it okay to short the output of an OTA? Maybe I made a mistake. Maybe this shouldn't be Phi1. Anybody? Philip? Is it okay to short the output of an OTA? Anyone else? Gigi, is it okay to short the output of an OTA?
Yeah, I think so. Because phi 2 is open.
Well, if this were an op-amp, would it be okay to short its output? Did you say yes? If it were an op-amp. No, right? You don't want to short the output of an op-amp. In fact, there's a short circuit prevention circuitry built into the op-amp that detects when you short it and shuts down the op-amp, right? Because an op-amp has a voltage output, so you put a short on it, it's going to draw a lot of current. Well, this is an OTA. An OTA doesn't have a buffer, and so if you put a short, what happens? Nothing special happens, right? It's a current source output. So if you short a current source, right, all the current goes into the output. That's fine, but nothing bad happens, okay? So sure, this is perfectly fine. Also, this capacitor CF, we should draw it, is grounded on both sides, right, during cycle 1. So in other words, this capacitance is discharged. So what this circuit does in phase 1 is it takes any previous charge on CF, discharges it, and it puts an amount of charge, let's say QS, onto this sampling capacitor, equal to, proportional to the input voltage. Okay? So in phase 1, what we're doing is we're actually capturing the input voltage, sampling it onto this capacitor, and then in phase 2 we're going to do something with that signal. Okay? That's clear to everybody? So now let's look at phase 2. So in phase 2, the input is disconnected, right? This switch is open, so there is actually no input. The capacitor CS is grounded on one end. This now is open. This is shorted to the amplifier. These are open, and so actually we get a feedback CF CL. So in fact, in phase 2, the circuit looks a lot like the way we want it to look, right? It looks a lot like our amplifier, except we had a charge QS at phase 1 across this capacitor. What happens in phase 2? What happens to QS phase 2? Because what happens to this charge? I have a capacitor. One end is grounded, right? What's the other end? So what happens to the charge sitting on this plate when I short this to ground? It goes away, right? It discharges it. So the top plate charge goes away. What about the bottom plate charge? Where can it go?
Shared by the CS and the CF.
Is it going to be shared? Okay.
First, it's kind of continuous, but then it's shared by the CS and the CF.
Okay. Someone want to refute that? Hint, hint. Okay. You seem to be shaking your head.
The feedback is going to try to force that negative terminal to ground, so it's going to transfer its charge onto CF.
That's right. So this charge here, it can't go into the op-amp, right? Because this is high input impedance. And because I have feedback active, this node is going to be forced to ground, and that means this charge has to transfer over here. So in fact, in phase 2, the charge of this capacitor, sampling capacitor, goes to 0, but it gets transferred to, let me draw this in this direction. So it gets transferred to the feedback capacitor. And so the charge on the feedback capacitor in phase 2 is precisely equal to QS phase 1. Okay? Any questions? Anybody see an approximation in this? Certainly for ideal case it's right? Yeah, okay. Okay, well, in phase 2, the output voltage is really from this terminal to this terminal, which is ground, and so V out is V across CF, right? And so if I go back here and write down some equations, this is equal to CS times the input voltage, right? And V out, which is CVF, I can also say QF phase 2, or QF always, is CF times V out. Actually in phase 2, because that's when V out is connected across here. And so if I just substitute CSVI, I have that V out over V in is CS over CF. Okay.
Why don't you ignore CL?
Why did I ignore CL? Because it didn't have any role to play, right? CL just charges up to whatever V out is. The charge on CL is maintained by this amp, right? Good question. Whenever you draw a switch capacitor circuit, start asking yourself, what about the other capacitors, right? Very important to look at all the capacitors in the circuit. First of all, did I mess up? Should this be negative CS over CF? Anybody? Kevin, you're sitting up here in the front. You're confident. Should this be negative CS over CF, right? Because then this is just an inverting amplifier. You're going to say no. Why? Well, you know, if you look at the math that we did, we didn't really make a mistake here. There was negative charge here, and it got transferred to the negative charge here, right? So you're right. This answer is correct. But why is it that it's not negative, right? This looks like a negative gain stage. Okay. Michael?
Yeah, you do the inversion with the flipping of the input capacitor, basically.
That's right. So look at this input capacitor. It's connected across this as basically it's inverted. The plus top plate was grounded, the bottom plate was presented. If this were a regular amplifier, right, then you could see that definitely you would get inversion, because then this would be the top plate and this would be the negative plate. But what I've done is I've actually flipped the capacitor over. In this process of grounding it, I'm actually flipping the capacitor charge, and so I get a non-inverting input. Okay? Good. So that's how a switch capacitor circuit works. Why is it that these circuits weren't popular with bipolars? It really took CMOS to make switch capacitor circuits popular. Simple question. Why not do this with bipolar? Yeah.
CMOS has good switches?
Yeah, we don't have good switches in bipolar, right? Bipolar switches have offset voltages. So you can turn it on and off very well, but you always end up with an offset voltage. What other property of CMOS is pretty important here?
Base current.
Yeah, the base current, right? If we look at here, if this thing had input current, then it would kind of mess up the charge here, right? So, great. This is an oxide, right? It's gate oxide. There's almost no current flowing into here, at least for relatively long channel devices, right? Nowadays, we've got tunneling current to worry about, so that things do change a little bit. Okay, so this is the simple picture of a circuit operating with two different clocks and using switches, and it's a simple basic building block that we're going to use in these kinds of circuits. So here is an operation of the circuit. Actually, let me use the next plot. Just to give you a reference, these are the clocks. So the blue clock is phase 1, and the pink clock is phase 2. And then let's zoom in on the various voltages in the circuit. So this blue line is the input voltage, okay? And the pink line is basically twice the input voltage. So this is the ideal, let's say, op-amp using continuous mode would generate this output. And then what we have here is this is clock 1, and then this is the output of the circuit. So you can see the output of the circuit. Well, first of all, let's look at the red line. The red line is Vx. Node Vx is this node here. It's the negative terminal of the amplifier, and you can see that it's grounded until you connect that capacitor. So at the end of phase 1, right, when on the falling edge of phase 1, that capacitor introduces a voltage onto this negative terminal, right? So at the beginning, the op-amp is not doing anything, right? So what happens is that this voltage basically drops down. It drops down in a step-like fashion because this op-amp can't respond instantaneously. And how much it drops down, how much will it actually drop down? Will it drop down a full V input? Why not? Somebody use a mic.
Because the charge is shared between CS and CF.
Exactly. At this point, there's charge sharing. So this charge will actually appear across both capacitors, and so this will be something proportional to V in, but not exactly equal to V in. Okay? So let's look back over here. So this is the negative terminal of the OTA, and you can see that as the op-amp settles, as the OTA turns on and it settles, it brings this voltage back down to 0. And while it's doing that, you can see the output voltage is settling to some value. Now I'm a little bit puzzled. Why is it that the OTA is not settling to the right voltage, right? Looks like there's always some kind of error. So here, at the end of this period, instead of being twice, it's just shy of twice. Okay, maybe there's a little bit of error built in. How about over here? Over here I settle to this value where I should be settling to this value. What's going on? Christian?
You're sampling, so there's a delay between when you sample and when you output?
Yeah, exactly. Very simple. So what value, what time period should I look at?
The phase 1 at the end of the phase 1, the falling edge of phase 1.
Precisely. It's the falling edge of phase 1, because at this point, so up until this point, the CS is actually being charged to V input. And if it can charge fast enough, it's essentially following V input. As soon as that edge falls, I've captured this point. So in fact, let me see if I can turn on the pen here. So here, this is the value that I should be capturing. And in fact, if you check it, you can see that, yep, that's right. How about over here? So here's phase 1 clock drops over here. So I should be capturing this value. And in fact, that's what it captures. Again, phase 1 clock drops here. And so this is the value I should be capturing. Okay, so the circuit works. It's actually taking the input and multiplying it by 2. Okay, questions, comments? Okay, now the most important thing, noise. How much noise are we adding in this process? Okay, and we're going to make use of these diagrams. So let's come back here. So let's first of all look at, whoops, wrong picture, phase 1. How much noise am I generating in phase 1? Okay. Well, I know that at the end of the day, the output voltage is the amount of charge on capacitor CF, right? So during phase 1, do I add any noise onto CF? Okay, some people are saying no. Why is that? It's grounded. Okay. Anybody have another solution?
Well, I mean, ideally, it should be grounded.
Okay, ideally it should be grounded. Anybody want to say something differently? Okay, it depends on if thermodynamics exists in your ideal world or not. But if thermodynamics are around, no. In fact, if you go into the lab, I'll give you 5 capacitors, and I'll tell you, go in the lab and discharge them. Okay? What voltage are you going to end up with? You're not going to end up with 0, right? It's going to be some distribution. What's the variance of the voltage you end up with? Anybody? Yes.
It should be a function of the parasitic capacitances through which you discharge the capacitor.
Well, let's say there are no parasitic capacitances. What? Yeah, you're close, right? What value do you expect to get? You get what? Okay, it's temperature dependent. That's right. But just give me a number, right? KT? 4 KT? Well, first of all, it's going to be a voltage, right? So 4 KT times what? Four KT times the capacitance? That doesn't give me a voltage. Parasitic resistance of the capacitance. Okay, that's a good guess, but no. You're saying 26 millivolts. Hopefully it won't be that bad, right? That would be terrible. Okay. Come on, everybody knows the answer. You guys are pulling my leg here. It's just KT over C, right? KT over C. How is this different from what we talked about before? So what I'm doing is, this is the R switch, right? And so I'm shorting my device with this R switch. Now you had a good guess. You said it's going to be 4 KT R switch, but that's the spot frequency, right? At the end of the day, when I'm done, there's just going to be a voltage across here, right? Because then I open the switch. And so when I open the switch, the noise that stays here is going to have variance KT over C, right? This is no different from the sampling problem that we looked at several lectures back. The neat thing is that, as before, the answer is independent of the resistance of the switch, right? It only depends on the capacitance, because smaller this resistance is, the wider band this is, and the more noise we integrate, right? And so, again, this is a philosophical question that you can think about maybe when you're walking home today. What happens if I have an ideal switch, like you suggested? If the switch has 0 resistance, final answer doesn't depend on the switch resistance. So what's going on? Okay, so think about that. All right, so now let's come back here and look at the noise sources in phase 1. So definitely in phase 1, we're going to end up with a little bit of noise voltage here, KT over CF, right, with variance KT over CF. And then how about the noise voltage on this capacitor? Anybody? Not a trick question. Anybody want to just say the answer so we can move on? Yeah, KT over CS. Actually, you're wrong. No, you're almost right. In reality, I'm not going to drive this with an ideal voltage source, right? I'm going to drive this with another amplifier. So actually, in phase 1, I'm going to have an amplifier driving CS, also in some feedback configuration. So we analyzed this problem, and we found that instead of getting KT over C, the noise you end up with is KT over C times some factor, NF, right? And NF is the extra noise of this amplifier. That's because, again, the output impedance of this amplifier is not equal to the noise resistance of this amplifier. And so you get this extra noise factor. Okay? So we can write that the noise, so during phase 1, we have noise across the sampling capacitor, which is kT over Cs times some NF. This is the amplifier driving Cs. And then the process of discharging that capacitor leaves a residual voltage with variance kT over Cf. Okay? Now let's look at phase 2. So, what happens in phase 2? Yes, question.
Yeah, again, you kind of ignore the CL.
I'm sorry?
You ignore CL because you are discharging CL too, right?
Yeah, remember in phase 1, that's a good point. Let's assume that in this phase CL is not connected. So, okay, very good question. Why did I ignore CL? Let's assume that I actually have another switch here, and I'm going to now at the very end sample the signal onto this switch, okay? And then we'll consider the noise of CL as well. All right, good point. Okay, so what are the noise processes in phase 2? Well, at the end of phase 2, as you pointed out, I'm going to take all the noise, right, and just sample it onto this capacitor, right? And so what I need to know is how much noise I'm generating in the circuit during phase 2, but all the noise also from phase 1 is also going to contribute, right? That doesn't go away. So the noise of on this capacitor due to the discharge process actually just adds to the output, right? So I'm going to pick up this noise. How about the noise on this guy? What's the transfer function from here to the output? Let's use superposition, right? Just the gain of this amplifier, right? Which is Cs over Cf. So I'm going to get the noise of this guy times Cs over Cf squared plus the noise of this guy plus any additional noise generated by this amplifier. So I could say that phase 2, I'm going to have just the kT over Cf noise, right? That directly adds to the output. Then I'm going to have the kT over Cs times NF noise multiplied by the transfer function Cs over Cf squared plus the additional noise. Okay. Now, do the first two terms make sense to everybody? Clear? So the additional terms are a little bit messier, and I'm debating if we should do it in a few minutes or not. Okay, we'll come back to this, but let's just give the answer, and then we can look at it in more detail. So to find out the additional noise, all I have to do is assume that these are noiseless now, right? Superposition, and just consider the noise of this transistor. So one way of doing that is I could include the input referred noise voltage of this guy and calculate the transfer function to the output. Okay? So if I do that, I need to also take into account CL at this point, because at phase 2 I'm assuming that I'm sampling all of this noise onto this capacitor and hopefully some signal. So at the end of phase 2, so the additional noise is going to be kT over CL, right, just as you pointed out. But there's going to be some extra factors. And one factor is due to the fact that I'm using this amplifier. Let's call this NF2. And another factor is due to the fact that this amplifier is actually being used in feedback configuration. So this is due to the feedback. And if you actually looked at your notes very carefully several lectures back, we found that this feedback factor has a form like this. Okay? So first of all, it's not just the feedback of the amplifier, it includes a parasitic capacitance on this node. Okay? And I guess we'll have to wait until next lecture to talk about this. All right.